Hi guys. Well, just like that, we're already in week 4. So this is going to be the first video from week 4. Week 4, there's going to be 2 informational video lectures, and I may or may not do a third video on the review for exam number 1. But this week is week 4. This is video number 1. So this video and the next video are all about chapter 5 from your book, which is called Nuclear Chemistry. So let's go ahead and just get started. This is chapter 5 from your book, Chem4, week 4, video number 1. All right, so chapter 5 in your book is all about the nucleus and nuclear chemistry. So we're not talking about electrons at all in this chapter, really. So first, some definitions. There'll also be some key terms and some new terms that you haven't heard about before, so we're going to go over those first. But the nucleus you have heard about before, and the nucleus is not of primary importance to chemists because the chemistry of atoms is generally determined by the number and arrangements of their electrons. However, in this chapter, the nucleus is going to be important. So it says there, but the nucleus and its chemistry has a big impact on our society. Things that I think about that are big impact on our society are nuclear energy and things like fission and fusion and how to find alternate sources of energy, right? So the nucleus, this is a little bit of a review at first. The nucleus contains protons and neutrons. The nucleus is very small, so the nuclear radius is on the order of about 10 to the minus 13th meters. So that is incredibly small. Okay, a nucleus is almost as if it's so small it's almost non-existent, even microscopically. So to put things in perspective about what I mean by the word small for nucleus, if a nucleus were the size of a ping pong ball, the nearest electron would be about 1/3 of a mile away. So if I'm holding a little ping pong ball, right, that 1s1 electron is about 1/3 of a mile away. It's very, very far. The nucleus is also very dense, and we'll talk about that on the next page here. So regarding the density of the nucleus, okay? Well, when I think of something that's dense on the periodic table, I think of like, maybe like lead, okay? Pb is probably one of the more dense atoms. So lead has a density of 11.3 grams per centimeter cubed. The density of a nucleus, however, is 1.6 times 10 to the 14th grams per centimeter cubed. That is a ridiculous density that you and I cannot fathom. So that ping pong ball sized nucleus, if you had a nucleus that was the size of a ping pong ball, that little tiny ping pong ball would weigh 2.5 billion tons. So it's out of the stretch of our imagination just how dense the nucleus is, okay? Those protons and neutrons are really in there tight. All right, next topic. That's why I've got those little double lines there. It means I'm moving on to something else, or at least something, same topic, but a different agenda. So the energies involved in nuclear processes or nuclear reactions. A nuclear process is just a nuclear reaction. The energies involved in nuclear processes or reactions are millions of times larger than typical chemical reactions. So the typical chemical reactions that we talk about in chemistry are not nearly as large or as powerful or as energetic as quote-unquote nuclear reactions. Some new definitions that we're going to need in order to talk about these nuclear reactions. Nucleons, okay? Nucleons is a particle in the atomic nucleus. So a nucleon is either a proton or a neutron. A nucleon is just a proton or a neutron. Atomic number Z, we've heard of this before. This is the total number of protons in that atom or that element. Mass number A, we've heard of this before when talking about isotopes. There's a lot of isotopes in this chapter. Mass number A is the sum of the protons and neutrons together. All right. So now moving to the top of page 3 of today's notes. Isotopes. This is another definition that you're familiar with. I just want to go over it here because all of the reactions and the way that we write nuclear reactions in this chapter we're writing down isotopes as we go. Isotopes, atoms of the same element having the same number of protons, of course. If you're the same element, you have the same number of protons. So it's atoms of the same element having the same number of protons, but different numbers of neutrons. All right? So if you remember from the previous few lectures, this is the nuclear symbol notation in the box. And then carbon-12, carbon-14, that is hyphen notation. So carbon-12 or carbon-12 is just 12,6C. Carbon-14 is 14,6C. All right? Now, another new term for you, not nucleon, we just learned about that one. Nucleon is a proton or a neutron. A nuclide is a term used to describe a particular isotope. So carbon-14, carbon-14 right there in that example, that is a nuclide of carbon. Carbon-13 is a nuclide of carbon. Carbon-12 is a nuclide of carbon. All right, now to a new topic because I got the double lines. I even got the star with the circle. Moving on to something else that is going to come or develop off of what we've just talked about. So nuclear stability and something called radioactive decay. All right, some background information first. Many nuclei are radioactive, which means they can decompose, forming another different nucleus and producing one or more other particles. Okay, so nuclear decay or radioactive decay is when you have a nucleus that can decompose and form a different nucleus plus a few other particles, which we'll talk about. So the example I have in the box there, that is carbon-14 decaying or decomposing to nitrogen-14 plus that little zero minus 1e. That's called a beta particle, by the way. It's an electron. So first, the blurb, it says Z and A values must be conserved. So if you look at the top row there, you got 14, 14, 0. And then on the bottom, you got 6, 7, minus 1. So on the left, it's 14 total. On the right, it's 14 total. On the left, it's 6 total on the bottom. On the right, it's 6 total on the bottom with the 7 minus 1. That's what they mean by conserved. Total A's on the left is equal to the total A's on the right. Total Z's on the left is equal to total Z's on the right. All right? And then that last particle is a beta particle. It's an electron. We'll talk more about that in a second. All right. Next page of our notes at the top, we're going to talk about different types of radioactive decay. There's a whole bunch. We won't go into all of them for this course. There are two main categories, the very simple categories. They are categories, the first one is those types of radioactive decay that involve a change in the mass number A. And then number two is those that don't. All right, so let's say that again. Types of radioactive decay. There's two main categories. First category is those that involve a change in the mass number A of the decaying nucleus. And that decaying nucleus would be your reactant. It'd be like your one reactant. And then those that do not. So first I'm going to talk about number one, and those are radioactive decays or nuclear reactions that involve a change in the mass number A of my starting material, of my decaying nucleus. And that first example is alpha particle production. That means I'm going to produce an alpha particle. What is an alpha particle? An alpha particle is just a helium nucleus. We're not going to count the 2 electrons. It's just the nucleus we're talking about. So it's a helium nucleus, and that helium has atomic number 2, so it's got 2 protons. Plus, if you look at the mass number 4, it's got 2 protons and 2 neutrons in the nucleus. That's all we're talking about is that nucleus. Anyway, some examples. 238-92U, that is uranium-238 breaks down to thorium-234, thorium is TH, plus helium-4, which is a helium nucleus, that's an alpha particle. Next example, thorium-230 goes to, that is radon, that's radium-226, plus helium-4, where helium-4 is my alpha particle. Now, the second type of radioactive decay reaction that involves a change in the mass number A, again, number 1 at the top of the page, is called spontaneous fission. And this is a splitting of a heavy nuclide, that means a heavy nucleus, if you will, into two lighter nuclides with similar or smaller mass numbers. So it's kind of like splitting splitting your starting material in half. And we see that there with californium-254. We'll talk more about spontaneous fission later on in this particular video, I believe. Now, number 2, these were examples where the mass number does not change. Okay? So, beta particle production. Actually, I believe number 2 is where the mass number, does not change. Okay, so beta particle production. An electron is produced. Remember, an electron is a beta particle. So if a beta particle production, that means a beta particle is being produced or formed, then we're forming an electron here. So the mass number A of the decaying nucleus remains unchanged. So I had that wrong. This number 2 refers to where the mass number remains unchanged or stays the same. And you see that with the thorium-234 and the Pa-234. So it does not change. All right, so we have that fixed. Good. An electron is produced. Okay, it's a beta particle, has a mass number of 0. Electrons have no essential mass, right? So the second one, iodine-131, turns into or decays to xenon-131, plus we have the beta particle produced. Beta particle is synonymous with electron. Okay. Now the second type, see, we did 2 reactions for number 1. This is the second reaction for number 2. This is electron capture. This is where we write the electron as a reactant. It's on the reactant side. It's on the left-hand side. So we have mercury-201 plus an electron turns into gold-201 plus that weird-looking symbol. Okay, that's actually a gamma ray. It's got no charge, no mass number, so no Z, no A. Don't worry too much about that. All right, so let's do some examples of balancing equations. Write the balanced equations. Bismuth-214 produces or emits a beta particle. So you just simply write bismuth-214 as your reactant. You write a electron product, and then you realize, well, what's left? Because the A's on the left have to equal the A's on the right. The Z's on the left have to equal the Z's on the right. So I've lost the screen now, but I believe it was PO, right? Polonium is your other product besides the electron. Okay. Let's do another example. We have 237-93 NP. I believe this is neptunium. So this is neptunium-237 produces or emits an alpha particle. Remember, a beta particle is a 0 minus 1e, an electron. Alpha particles are the 4-2he. Okay, so that's what I've written there as my first product. So neptunium-237 goes to helium-4, that is my alpha particle, plus whatever's left, because I have to make the A's and the Z's match up on the left and right. So I do that, I get 233, and then a 91, 233, a 91, and a Pa. I believe Pa, might be wrong, is Pascalium, I'm not sure. All right, example, fill in. So we have Au-195, that's gold 195, plus something, gives me platinum-195. Well, you see how the 195 on the left is already 195 on the right? We're going to have a 0 on the top there in the question mark box, and then a -1 would take the 79 down to the 78 that's in platinum. That's where we get 0 minus 1. This is electron capture, okay? All right, so we've got alpha particle production, beta particle production, electron capture, and the fourth one is spontaneous fission, which I said we would get to later. 4 types of reactions, really only 3 that you have to predict products on and fill in stuff. All right, radioactive decay series. Now, a series is like when you watch television, you're watching more than one show. Well, a radioactive decay series is going to be when a radioactive starting material is going to decompose in a series of steps. So radioactive decay series. This occurs when an unstable nucleus, right? If something is radioactive, it's unstable. It's going to decompose. It has an activity, they say. Radioactive decay series occurs when an unstable nucleus cannot reach a stable state through a single decay. So that means you have an unstable starting material, such as uranium-235. Through a series of decays, uranium-235 becomes lead-206, and lead-206 is stable. All right, now half-life with a little t1/2. Half-life is a new term, as of right now. It's defined as the time it takes, or the time required, for the number of nuclides to reach half the original value. Basically, half-life is the time it takes for half of your starting material to decompose or to disappear. How long until half of what I start with is gone? Half. All right, so it says on that little bullet point, the half-lives of radioactive isotopes, or nuclides, can vary tremendously, from 10 to the 9th years to 10 to the -4th seconds, all over the map. All right, example, a sample of fluorine-18. See how I've got the 18-9F? A sample of fluorine-18, if you will. A sample of fluorine-18 has a half-life of 1 hour and 50 minutes. How many half-lives are going to take place between now and 330 minutes? Well, 1 hour and 50 minutes is equal to 110 minutes. So 110 minutes times 3 gets me that 330. I will have undergone 3 half-lives in 330 minutes. Okay. Another half-life example at the top of this page of our notes, it says a 120 milligram sample of technetium-99 has a half-life of 6 hours. 6.0 H is 6 hours. How many milligrams of technetium-99 remain active after 24 hours? When I say remains active, I mean how much of the unstable starting material is still left. Because an unstable starting material is a radioactive material, and radioactive materials are referred to as being active because they can decompose readily. So we have 120 milligrams. We go through 1 round of a 6-hour half-life. We're left with 60 milligrams. That's 1 half-life. 2 half-lives. Now we've gone through 6 hours twice. That means we're now down to 30 milligrams. We go through our third half-life. The third half-life takes me from 30 milligrams to 15 milligrams. And then a 4th half-life gets me to 7.5 milligrams. So if my half-life, looking back at the original problem, if my half-life is 6 hours, so you got 6 times what gets you 24? 4. So you got to go through 4 half-lives. Okay? So after 1 half-life, 120 becomes 60. After 2 half-lives, 60 is now 30, and then 15. Finally, it ends up at 7.5 milligrams. All right, that's all for this video. It looks like this is not the video where I talk about spontaneous fission. That's going to be in video number 2, which you can watch directly after this. That will be our last video on your chapter 5. And then we have everything we need for exam number 1, which is chapters 1 through 5 in your textbook. And I'm thinking of making a review video, which would be tentatively a video number 3 for week 4. All right, so enjoy watching this video, and then you got the next one right after it. Okay? All right.